All right. We're
Doing great.
you see the date
Oh, is it up yet? Okay, I haven't.
I've seen
Okay.
homework.
started?
No, because I was reading the textbook.
I'm gonna start tonight.
Okay, do you mind giving me a physical copy of your homework, Jim?
Yes.
It's just easier for me to mark. I mean, you can obviously have it in front of me if you have if you do work on iPad.
No, I'm ancient, sorry. I just drive you ready, everything like that.
Yeah, that's okay.
Okay.
Okay, so today we're gonna talk about complex integrals. And we'll talk about that in the context of, we've already done derivatives. And so the natural next step would be, how do you take an integral in a complex space? Right? So we'll have that discussion. We probably won't even, we won't spend a long time on it. So we're gonna do complex integrals. And then we'll talk about Cauchy's theorem for complex integrals. Of the same name of the, yeah, the Cauchy-Riemann, and you'll see that they are in fact related to one another. And then I think we're gonna skip over, I guess we have to do residue theorem. Okay, no, we'll have to do residue theorem. I was hoping we could get into applications of complex variables next Monday.
Okay.
But perhaps we'll need to sort of. We might go back and forth between some of the applications, because I know this has been a lot of theory for folks. Maybe folks enjoy it, maybe they're thinking to themselves, wow, this is really a lot of things without ever understanding how this could be applicable to math. So we'll see some applications when we start looking at the complex functions. Like specific complex functions that we end up using. Okay, so what's an integral?
Oh, just like the area under.
Area under the curve.
Area under the curve, good. Okay, so I just want to, right, because that is something that we've grown up knowing. And similarly with multiplication, what's multiplication?
I was gonna say the product of the two things, but that's just like saying.
Yeah.
Well, it's just like how many multiples of one number. And like, what's like the result of that?
Area of two numbers. I don't know what is that.
The area of two numbers, yeah, so that's maybe a geometric way of thinking about it, right?
Yeah.
And some people have learned, when you're a kid, you learned it's repeated adding, right?
Yeah.
Right, so like, what is 3 times 3? Well, it's 3 times,
Yeah.
right? So you have to add 3 to 3 to 3. And there's this great video that I saw recently that was talking about, well, how does that sort of an understanding break down when you begin to think about something that maybe you don't learn deeply in elementary school, like negative numbers. So what does it mean to multiply a number by something that's negative?
I was thinking like in like a 2D plane, you like go the opposite, you go the opposite direction, the positive point.
Yeah, it's like certain direction now.
Okay, so you think of it in terms of directionality, but of course, we're talking about numbers. Right, so you have a number line.
Yeah.
Right. Positive numbers out here, negative 0. Right?
Yeah.
Okay. So what is multiplying a number by 2 do?
Oh, it's basically
It doubles it, right? And so it's the idea of scale. And so one of the things that we want to walk away from is some of our notional ideas. We started off by talking about what is an integral. It's an area under the curve. And that's certainly true when we think about it in the context of, say, real numbers, right? So here's some function, right? F of x. Here's x. What's the integral of x?
it's just like the region between the curve and the x-axis.
Good. Okay. And that's sort of how we interpret these things. We'll need to rethink how we interpret integrals. Let me show you why. See the problem yet?
So it's like. You're measuring how real or unreal this.
Well, so let's say we have a function f of z function. Right? How do we define the integral now?
Well, I think it would depend on where the branch point of like where the function, if there is a branch.
If there is a branch point, big assumption, right?
Yeah, so if there is a branch point,
Let's say it's single valued everywhere in analytic.
in a single value, okay. Are you still talking about like what the integral of this is, or like?
Yeah, how do we think of the word integral, right? So integral, you said, has an English meaning, the area under the curve. Similar to how we think about at this position here. Right, this would be f of x prime, that would be the slope,
Yeah,
right? So we have these connections to these operations that we know and love. And just as I showed you before, we cannot take for granted that these will map in our minds our understanding of such a thing into this other world. Because we saw, for example, let's say I want to take the integral and I want to take a path, sorry, the integral, I want to take a derivative. And I want to take a path that goes to 0 this way versus going to 0 this way versus going to 0 this way. Right? As the limit as the dx, dy goes to 0. Now, what did we find out about those derivatives? Sometimes.
What, like singularity would occur at 0 or?
Not necessarily as singular, that's how you can see if the function is defined.
Okay.
We're just talking about the function, right? You define, how do you define the derivative?
It was the limit,
Yeah, the limit of
well, in this case, x approaches.
Z is enough, is enough.
dx and dy
Y.
going to,
Is-
good, okay, right, and you know the rest of it, right?
Yeah,
So this is the part that matters. So as dx and dy head towards 0, what did we find out about the derivative?
oh, that it changes depending on, in some cases, like, if delta z was considered 0, and then you only take the limit as it approaches del y. For
Right.
0.
So we found that it was path dependent. Right? In complex space R f prime of z can be path dependent. That wasn't super unusual because we kind of saw this with discontinuities when we think about a function in the real space, that it can have a discontinuity heading from one direction versus the other. But now we see that there's a problem, right? Because when we think about this in the context of f of z, I should read f not of x, but f of z. So when I think about this in the context of f and z, this is being represented by something that is similar to, but not a 2D space. Right? So now when I ask the question, what is the area under the curve? It's not really meaningful.
Would we have to do the area close to,
Why a closed loop?
so then it would be easy. The area would stay the
So you're saying I could never ever do an integral unless it was a closed loop?
well, I don't know.
I mean, I didn't do a closed interval here. You're saying that in a complex space, I can only take them between bounds? Right, that'd be very, very restrictive. Right? So we have a problem in understanding what's going on here in a complex space. Does that make sense? Okay. Let's see if we can resolve. That'd be my job. Okay. So, we'll leave that up so that we can see the similarities here. That okay? Okay, so let's pick some points A and B. Okay. So what is A?
Negative real components, negative imaginary components.
But it's a number, right?
Oh, it's a number.
Yeah, it's a real complex number, or it's a real, negative real part, negative complex part, and it's a number. Okay, and I wanna go over here to another place called B. And that's just different number.
Yeah.
So I'm integrating from essentially A to B. Right, that's my claim, I want to be able to do that. Okay. And let's make this really simple on ourselves. We're going to connect those two lines. That makes sense. Okay, so I connected those two lines. That choice was weird, Grismani, I don't know why you did that, okay? And then here's a little arrow showing the direction. Okay. So these 2 points are connected in complex space. They're connected a number of different ways, but I'm going to start with this one. Okay. So let us now imagine, and you need to use your imagination here because there is no time. Okay, but let's imagine there was us following this path. We live at A, we're walking to B. And the complex space has hills, it has valleys, whatever. Okay, and we're walking. Okay, this is the path we're taking. So we're gonna say 2 things. We're gonna say X is going to be a function of something called T. Not really T, not time, but think of it that way, okay? Y is Y of T. Okay? You start at A at alpha, or I should say T equals alpha. And B at T equals A, okay? And let's call this path, for lack of any better letters, C. Okay. One requirement that we're gonna say is the path C traverses a continuous okay. And so therefore we can write, this is the definition of the integral f c, that'll be the path C here of the integrand f of z, and then a small step that we take in that real space, or sorry, in that imaginary space. Did I confuse anyone yet?
Not yet. Also,
Okay, so how can we rewrite f of z? What are the definitions of f of z, by the way? In terms of other things,
X of T or
Sorry, U of X, Y
u as a function of x, y,
plus I, V magnitude of X, Y.
v,
Yeah,
good. Okay, good, I wrote that. How do we write dz in the same, taking into account x and y?
oh,
Well, let's look at the real space. What does DZ look like?
Or the dx. plus u. U,
Why is that?
this x is the root space, y is the.
Right, if this is a little space DZ, right? Then it must be equal to dx plus I dy. Is anyone upset that it's not dx squared plus I dy squared square root?
No.
Okay, good. Because we're not actually thinking of these as lengths. Okay, good. Okay, so let's rewrite that. Cool. What does that give us?
I'll show you. Yeah, the green integral.
So you're saying combine them together, we can do U X Y plus I of D X Y. Dx plus I D Y. That'd be times one.
So if we distribute that, we get a double integral, or we take one integral like with respect only to x and another one with respect only to y.
Let's be careful about our words here. When you say double integral, I usually think two of these.
That's what I was.
So how would I get a second one of these symbols?
So you're saying that
That makes sense.
what's the question?
I didn't ask a question.
Oh,
Well, what I was talking about was like, hey, if we distribute the del x and del y, distribute that, then we can kind of get like an integral only in terms of like deriving
Yeah,
dx.
like,
And
well,
another integral only deriving in terms of dy.
I mean, we definitely could,
well, you and both have x and y.
Yeah, that's what I was thinking, I'm just like, that doesn't make sense.
Yeah, they both have x and y, right?
we could
Yeah.
split it into two integrals.
Before intro.
Why four integrals?
Well,
If you do the like the u times dx. and
Yeah, let's do it. Let's do it. So u times dx, that's what you want first?
Yeah.
So that's this term times this term.
Yeah.
Okay, now what?
And u times I dy.
And then this one times this one. I don't like that as much. I'm gonna do this one next.
All
Let's see why. So what happened then?
Um.
Okay, and now what? Now I'm gonna go back to yours.
And u, like u. Or, yeah. And u,
I haven't done.
or u,
Fine. Then this one with this one.
Yep.
Huh. That's interesting. Okay. So now we said that we had some function, and I of course erased it right after, because I can never plan this properly. So this is what we define x as, and this is what we define y as. Right? So I'm gonna do something here. All my dx's, I want to turn into functions of t that I can integrate along the path.
dx.
Right, so I'm gonna use the dx dt here to turn them into the appropriate. Let's do the first one, c, u, what's the next? All right, add in here. How do I turn this into dt?
Dx over dt, right?
Good. Times dt. Good. That's not so bad, right? And now instead of the contour, or sorry, I had to just do alpha to beta like we talked about before.
Oh,
Is that okay? Okay. Now what?
Oh, sorry, alpha beta,
Oh, very good.
d times dy dt.
When was on. The beta. And dy for dt. Dt. Not one plus I non the beta. B dx. B.
Cool. We did it, right?
So the entire point of that was to just convert it from like complex to like this point of time.
Mhm.
Okay,
Yeah, we're not done. That was a
yeah,
joke.
this is it for this step.
So we now have a sufficient condition here that we need dx dt, right? They should be continuous. If dx dt or dy dt are not continuous, no integral, right? Okay. So this is apparently what we're going to be thinking about when we take these complex integrals. And I think in practice, it looks awful. Doesn't look very approachable. So let's do an example. And we're gonna look first at one path from A to B. Then we'll look at maybe a different path from A to B and see if the value of the integral changes. And we'll see what moving around in this complex space means. Right? I said that we made these analogies that we're traveling from one place to another. We'll see whether or not that comes out in this interpretation. So let's use a complex function and see if we can understand what I've just written. I don't know why I was so generous and thought that I would have gotten all of that onto that board, but let's write it. So let's start with a function f of z, which is 1 over z. First question, is that analytic?
everywhere except where z equals 0.
What happens if z equals 0? Singular. What kind of singular? That's what singularity means, but remember we talked about the pole of the singularity, do you remember that?
Oh, the polar singularity, isn't there just polar zero? Right?
Well, that is the location of the singularity.
Yeah, that's
What does the
location.
pole mean? The pole means how many powers of n are your zeros going with. Right, it's 0 to the power n. Here the n would be 1.
Okay,
1 over z squared will have a singularity pole of 2.
Okay.
You see, one of them goes to 0 faster than the other.
okay.
Finite constant, like the.
Let's go to 0. Head to z equals 0. Okay, falling down in full. Okay, which goes to 0 faster?
Oh, out of the 1 over z or 1 over z squared.
Right. So there is actually hidden in here some information. This is not 1 over z, this is 1 over z, it's at the end. And the n tells you about the pole of the singularity.
Okay.
And when we looked at these different examples on Monday, we saw that you could have, say on the bottom, multiple poles, multiple singularities, right? And maybe you have a singularity here that's of a certain strength, a singularity here that's of a different strength. You'll see this in the second pretty. Just fucked up problem.
Alright, so,
Okay, some of them are easy, but some of them aren't. Okay. So this is gonna be our function. And this is analytic, it has a pole. And we know what the pole is?
like the actual itself,
Sorry, the singularity, you know the singularity?
well, isn't it order of one?
The location of the singularity is at
0.
0, good.
Good.
Alright, so it's in the origin of this space. Okay. Yeah. The pole is just the strength of the singularity, so it's the end that's up here.
To the power of z, so that's z to the power of n.
Right? Okay, let me pull the definition back out so that we can see it again.
So you talk about like a pole order rather than the location of the pole, because I think for me, I'm used to like saying location of the pole. In like advanced electronics, but then like here is that just like equates to singularity.
I think I'm being a little callous with my words here. Okay, so let's just write them down so that I can be very specific and you can be like, Mateo, that's not what you said. Okay, f of z is equal to g of z, right? Some analytic function over z minus z naught n. So this is the order of the pole. This has a singularity at z naught. That's the location of the singularity. And an isolated singularity is the pole. This is the order. Should have specific. Pole. Pole order at z equals z. So let's retry that. Let's try that. Let's look there. So this one here has a look. Where is it located?
At zero.
Zero. And it's a
First order.
better. Yeah. Okay, so we know that if we go through the origin, we're gonna have a bad day. So how do you integrate infinity? Does that make sense? Let's perform some magic. Okay. Let's place here the information about our pole. Make it right there. Right? Bad. So let us do a path along a circle that is defined by z. Half value of z equals some distance. Okay, so let's do a circle around the origin. Okay, so this will be r. Whee! That's a really good circle. One of my top 5 circles of all time. It shows how badly I draw circles. Okay. Now let's imagine that there's a path. Okay. And let's imagine, you've heard of parameterization, which is where you talk about writing one thing in terms of time or in terms of some quantity that's going to be moving forward. So let's write z of t as we'll take advantage of the fact that this has not changing modulus, right? And the argument's the only thing that's changing. So let's write it in the other format. Let's write it like this. that okay? And I'm gonna allow E to do that. How did I get this line?
Not just the definition. Okay, words.
Yeah.
From what?
So you start off with,
E to the IT,
R magnesium.
Yeah.
R,
Yeah, exactly right.
And then you use oils.
Good. That better? With my sling right. Okay, cool. So, how do you define, say, f of z in this, real space, or sorry, complex space? Right, put on the bottom here.
So how do you write it in complex?
Okay, if I want to,
F and G terms.
so let's think about what we're doing here, okay? Go back a second, or right anymore. Go back a second. I would need to integrate this stuff. And you can already see that I've chosen a path. And if I look over here on the right-hand side, right, I have all these pieces. dy, dz, dt, sorry, dx, dt, dy, dt, right? Now I have a nice path, nice and smooth, continuous. Can probably take derivatives of that, right? Okay, so now I need to understand what these things are. U, V,
Okay, so, yeah, U would be the cos T and
R goes.
yeah,
no,
no, not the method.
Oh, because it's still in T, we need.
no, you're looking at the wrong thing. There is a path and there is a function. Let us recall what we are doing. We live in a complex space. In this particular circumstance, I am heading from my house. I'm going on a walk all around town, and I'm going back to my house. So I end up where I started. It's a closed loop. Don't get ahead of yourselves, okay? But the question is, we are going to do an integral. And the integral cares about the path, essentially, right? But what it does is it transverses the function. Right? The complex space means nothing unless you're integrating a function. I mean, I guess you could integrate a constant, that's meaningless, right? You do the complex integral of t, z. But remember what we said up here, this is what we want to find out. How do we take an integral of a complex function? And so inside of this space, we have this function. How does that function look?
Like ln of Z.
No, how does this function look?
In complex.
Just, you know, if you think about what is 1/x look like with your hands? What does it do at 0?
But
At infinity,
Oh, it starts at infinity, good,
Yeah.
okay, it starts up here, let's just use our hand, let's literally think about what we're looking at.
and then as it's going up, it's going down.
Okay, x equals 1, what is it?
It's just one.
One,
Good,
So.
it must have gone from here to here, that must be smooth, and then what happens?
so like half, to a third, to a
Like,
fourth.
so it's kind of,
Does it ever go below 0?
no,
Okay. What about on both sides? I did this with both hands, is that
Yeah.
true?
it's symmetric.
Oh, okay, good, so it's asymmetric, right? So there is some, wait, is it or not? 1/x,
Yeah, whatever, yeah.
has to be, right?
Yeah, 'cause it-
Okay,
you're-
so it has to do
yeah.
this. They're not friends, they don't talk to each other. That's just in the real part.
Yeah.
Okay, so then you can think about what it does in the unreal part. But you can imagine in this part of complex space, there is some topography. There is some places that go up. There are some places that go down, right? And our job in transversing the space, in walking the path, is to find out how much of the function we are adding up along the way. right? It's a path integral. Is that beginning to make sense now?
Yeah,
Okay, this is why the application is so necessary, because that doesn't make any sense, right?
yeah.
That barely makes any sense. You have to smoosh them together. Okay. So, I need to rewrite f of z in terms of u and v. Right. One over u plus iv? No.
You wanna go from P to C?
That's not what I said. I said we need to rewrite f of z in terms of u and v.
Oh, okay.
Don't look at T.
Functions of X and Y. you're talking about.
Yeah, don't look at t, don't look at where we're headed after that. I'm just asking for one simple step, which is that in order to take the integral, we need to know what u is and we need to know what v is.
So, at I1, R is equal. R is X, I1 is 0. Then,
Cause like my first thought is just U is equal to R cosine T. And then V is equal to R sine. T. That's my first thought.
yeah,
Wait, I think this is confusing. Don't look at t. Look at the function.
Oh, look at
This function needs to be written in terms of u.
so
And
you're talking
V.
about like Z is equal to X.
So hold on.
plus-
F of z is equal to u plus
I,
v.
Yeah, okay. That's, so we wanna make one over Z into that form. So it can be
Right.
one over X plus I.
Hold on. 1 over,
X. Plus I, Y, or L.
good. This is the first step. Now, why are you not allowed to simply say that that's done?
Cause there's a real component with the imaginary component. denominator.
Yeah,
So
denominators just suck, right? They're the worst. So how do we deal with it?
Partial fractions.
Okay, so what are we gonna do? Top and bottom?
X, minus IY.
And what's on the bottom?
X squared. Plus Y squared.
Yeah.
Oh. Minus, oh yeah.
No, because it's minus, right? Do we see that or not?
Yes,
Okay, so how do I write u?
Oh, so U is equal to X over X squared plus Y squared.
Very good. And
Plus, is it negative I? Plus negative I, Y over X plus Y squared.
yeah, I'm gonna do I out here. I'm gonna do negative y. Just to be contrarian. That's okay.
sure,
Okay.
Yeah.
okay.
Okay. Okay, so maybe that's where I should have started. So now let's discuss the path we're taking. Z as a function of t. Let's write that again. What was the first step? Was to say,
First up,
That's the R. E, or R cos T. Plus R, I R sine.
correct or incorrect?
so that gives you just like the circle path in complex plane.
Sorry, say that again?
That Z of T is the circle path of like complex plane.
Yeah, that's this.
Okay.
So this Z of T is the path that I take to leave my home in complex world. To go for a jaunt, maybe I pick up a hamburger, and go home. Hot dog, I should say. Make sense?
Yeah.
Okay, well, it's really convenient that this looks like this, and this looks like this, right? Where's X?
squared.
How do I define z in terms of x and y?
Well, it's x plus I y,
Very good, okay, we'll say that slowly, where's x?
x. R plus.
Very good. So this piece here, the real part of z is x. And this piece here is
Y.
correct.
Okay.
So this looks really good now, right? Because I can do x squared plus y squared and I'm gonna get r squared. Good. And that's gonna be on the bottom for both, and I can put the stuff on the top. So let's just rewrite this then. Okay. So this is gonna be what? On the top?
Oh.
Good, all over. Good. And then the next one? Close, you're just gonna. Good. And? Very good. All right, now we're fucking cooking, right? Okay, so we've defined our x's, our y's, our u's, and our v's, and we've gotten rid of everything that is not dependent on t. Okay. So we have an expression here. Right?
Oh, so we're gonna,
Do we need anything else?
y dt. X.
Yeah, let's write those down.
Component, you can take the t.
Write down those two.
Oh, we also need,
dy dt is what?
What?
dx dt is?
It'd be, negative IR cos of t.
There's never an I when we're talking about the x's and y's, right?
Okay.
Because this piece here just shows you that this section is the imaginary part,
Okay,
but it's always I, y, right?
Okay.
But I'm thinking just about y, we can ignore the I.
so it'd be a negative R cos t
Which one here? Or here?
for dy.
dy dt.
Right, the sign was a close, yeah. And then cos was a negative
Let's
sign.
go to sign.
Yeah,
Yeah,
yeah, so it'd be.
which one gets a negative?
Yeah, the cos gets a negative, so the sign would be positive, or you go to positive cos.
no, derivative sign is just cosine, but there's still that negative sign in the numerator, so negative cosine. So negative cosine,
Does this one have a negative? Or does this one have a negative?
That one up top has a negative, but the bottom ones will be positive, is positive cos. That's
wait,
right.
so which function are we? Okay, so, oh, I was misinterpreting which function we were.
Yeah, no, I-
was looking at f and c,
Okay, so this is u,
yeah,
this is v. This is x, and this is y. Here, I just want the derivative of y with respect to t, and that is
R cos t.
r plus t. And then dx dt,
That's the negative R sine t.
okay, so please do the integral. Anyone online? I'm gonna say you can each take one term, now I guess you'll have to be multiple terms.
so, look at the r cosine t over r squared, like that portion of it, that's still u and v. So r cosine t, r squared plus I, negative r sine t over r squared. That is u and v respectively. Like that's, that just still u and v, but it's for the t.
Yep.
Okay.
Yeah, so remember that the function here can always be written in terms of a real and an imaginary part. So even though we got this original function, which was one over z, which is one over a complex number, you can rewrite it in terms of these two parts. And of course, u is a
Is
function
equals.
of x and y, and x and y are functions of t.
Okay,
Right? So
good.
it's like a Russian nesting dolls.
That's-
And alpha majored is 0 into pi, it's still just a circle. We use u and v in terms of t for the integral, correct?
Because remember the derivative or
Yeah, integrate. But
Yeah.
still, okay.
What you got?
The first. Real components. Cancel out, I got post, d sine t dt, but it's a negative integral of that. Plus the integral of sine t cos t dt.
Let's not assume that they cancel out. Let's do the integral.
Okay, well, in that case,
What's the integral from 0 to 2 pi of cosine?
0.25 cosine.
cos
what's that?
t sine t, it's,
Say that in the back.
You said the integral, so
Yeah, what's the integral from 0 to 2 pi? Of cosine t sine t?
Yeah, it should be zero because it doesn't matter.
Yeah.
One is gonna be zero in one case and the other is gonna be zero.
Well, not
No, wait,
all
no,
times.
wait, yeah, you're right, sorry, 0 and 2 pi are the same equation.
But if you multiply them together. Right? Say that again.
I just said one's gonna be zero.
So imagine a periodic function like sine itself.
Yeah,
What's the integral of sine? From 0 to 2 pi?
I think it was. Oh, no, actually, zero. Well, if it's periodic, you're just gonna end up exactly where it is.
Mhm.
When, like, at that place, so it's like, everything that's it's like, try to describe it, I know what I'm talking about.
Okay, we'll do this, prove this for yourself on Wolfram later today. Do the integrals, right? Do integral from 0 to 2 pi of sine, 0 to 2 pi of cosine, 0 to 2 pi of sine times cosine. And sine times cosine over a full period is 0.
Because the areas of the curve cancel each other out.
Yeah, we're not gonna use that framework anymore, but that's the right way to think about it, right? Okay, so the first two terms, so here's f of z. Okay. Or sorry, I should say the integral. Of f of z dz. Is equal to 0 plus 0. Okay?
Yeah.
What about the next two?
I got, it was,
What?
They're both pi.
They're both pi, right? Because sine squared over a period is pi. And so is cosine squared. The answer is
2 pi.
good. So what have we done? We started at home in a complex space. In a location with some analytic function f of z. And we went for a circular walk. And we found out that we collected 2 pi. Is that what you expected? You went in a circle, so circles and pies, we love that. You don't have your real parts.
yeah, that's why I was confused.
Is that what you did?
So it's in the same place. So it's like.
Yeah, but if you end up in the same place, right? So for example. If I walk, right? Let's say I'm in a real space. And I walk over there, I walk back.
But we're also-
Oh, now we have, it's not really walking, right? It's a poor analogy for our mathematics, but it's what we have. Right? Okay. So that's the result. Now, we're not gonna do anything different here. But I'd like you to find out what the result is if I don't go all the way home. But I stop to pick up Costco hot dog. Can you do it?
True.
Oh, you did a contour integral? What?
Wait, what is it?
No, I mean, you have to use this, right?
I did, yeah,
So what are each of the pieces?
yeah, 0, 0. I, 5/2 plus I, 5.
So sine squared from 0 to pi is pi over 2. You're saying,
Yeah.
and cosine squared. Okay, that's right. I thought that you just put the actual complex integral in,
No, I put them in.
which you can do, by the way, but you won't learn anything. Okay, so your claim, we'll see if anyone else agrees. Is that going to pick up the Costco hot dog? Let's call this path. It's gonna be right along the same way. I'm gonna call this C2. And the integral of C2 of f of z was I pi, is that your claim?
Yeah.
Okay. So now let's say that I don't want to be boring anymore. And I just need to like stop to get gas, and then I need to go. These are really bad analogies, but I'm just trying to motivate something in this class. I need to stop to get gas at some location on the imaginary component, and then I'm gonna go get my Costco hot dog. But I'm gonna do it straight. So now I want to start here. I want to go here. And then I want to go right back down to here. Okay, let's call this C3.
Hey.
Now, first thing to think about is, this is still true? Right? This part's still true? Well, what do we have to change?
The,
Bounds of integration? Still start at this point and you still end over there, right?
Like we're at straight line.
Right, so that's not the bound.
function. That function itself.
The function is up here, that's not changing, that's still the topography.
Oh, we're not using,
What has changed?
The relation between X and I, Y,
X and I,
right? Because now it was going like this, where R was constant, and now it's going, R is changing.
Oh, I see what you're saying, okay, okay. So you're thinking about this,
Yeah, oh, yeah, okay, okay.
the path Z that we trace out with time. The path that I walk is changing,
Yes,
good. Let's call that first one, let's call this C1. Okay. How to define this path now?
I need to. We have to change the boundaries of integration. So,
X is equal to -5.
Sorry, folks, I want to walk from here to here.
Yeah.
I need a path. How would I do that?
you're
I
gonna
mean-
take a C3 path, for instance. Well, you're gonna need some path.
You have to make two different functions for each section.
Correct.
Yeah, so
Because it's not a continuous function, right? There's discontinuity right there at the top. So between one location and another, I'll need to define it as a
Piecewise.
Sure, but from one location here, it'll be a,
One integral and then the other one is,
what kind of function?
A linear function.
A line.
yeah,
So it's a line from here to here and a line from there to there. Okay, that's all I need you to do, right? So we're not reinventing the wheel here, right? We're not gonna overestimate it. All we're doing is we're saying z of t from this time to this time is a line. And then from this time to this time is another one.
Yes.
Okay, good. Okay. What's the first one?
I just. So, I guess, okay, so when Z to P one, are we just trying to make the line in between, like, from the order, from the starting point to, like, the vertical axis? Okay, so wouldn't it just be like the x component would be r? I'm trying to make this a form of like x plus iy, or like,
You don't have to do that.
okay. Well, if it's just like, well, if it's just a linear line. And
Yeah, first connect them, then you can move them around that. But all I care about is just the line. How does x change?
Actually, with like a slope.
Yeah, so you gotta parameterize the equation. In terms of t. You get that,
Yeah, let's imagine, let's do the easiest possible thing. Okay, let's choose a variable t, let's say t1. Starts at 0 and goes to 1. Okay, so we're gonna take the integral from 0 to 1 of t1. Okay, so let's use the simplest parameterization. And t equals 0, what do you get?
t,
Like sugar line.
R, good. All right, and then what happens to the x component here?
Start decreasing here, yeah,
Good.
okay.
So how do I write that?
Decreasing
What
here,
happens at t equals 1?
equals 1, that's where it's. So t equals. That, oh, x has to be 0.
Right.
it's 0.
Paul said the word,
Yes. Like,
the line,
yeah,
linear.
so we need a slope.
1 minus t, line. Right? Does that have the right bounds? When t equals 0, what do you get?
Yeah, when t equals 0, you
R.
Yeah.
What happens when t equals 1?
get 0.
Which is what you want, right?
Yeah.
Deeply overcomplicating things here, folks, right? It's a line,
Yeah.
okay? Okay, next one. What does Y do?
Y has to increase.
Good,
Yes,
so what?
to R.
Good, so what do you get? There we go, that was way easier, right? Okay, now let's reverse the process. Okay, so between E2 and 1, I have Z, T, and I'm gonna write it carefully here. Okay, so now this is E2, how do I get it?
Shouldn't it just be R from T? Yeah, R times T plus I.
What?
Oh, because it's a negative, so that's a decrease to negative R. And
And
negative
when I
R.
write it, I wrote it, yeah, R on the front. Okay, now?
I type R times 1 minus T.
Agree? Pulling teeth sometimes, folks. Okay, can we do this? Can we do these intervals?
Yeah.
Yeah, it should be pretty straightforward, right? I don't think we can finish this in time. Let me show you, it's not a trick. But it's, you know how you do things a bunch of times, and then you're like, oh, that makes more sense now.
Yeah,
Okay, so let me ask you to write it in this way. Write the integral of C, what is this, 3? Of BZ over. What am I integrating here?
dz over dt times dt, right?
No, just what am I integrating? What is the function? 1 over Z. Okay, let's just start here. Okay. So we're gonna write Z in terms of some other stuff. Right? Make sure that you write here one integral of the first half. Let's call it C3 1. Okay, something plus the integral of the second half C3 2 of something. Okay. These will be dt's. This will go from
One, also convertible.
I don't know that we'll be able to finish the details. I'll let you think about them. Let me know what you find out for C3. Just thinking about this for 1 second, like you put your pencils down, stop thinking about the actual mathematics, and I asked you a question at the beginning that was about what the fuck does an integral mean in a complex space, right? Is that correct?
Yeah,
And I said we started at our house, we walked around, we got back to our house, we found out that we collected I2 pi. We didn't know what that meant. Now we get a Costco hot dog and we collect I pi. Now I take a different path. Right, and I walk or I drive or whatever, go up to see my friend at IY and then I come back down to get the Costco hot dog. So look at these two paths. Look at C2, maybe I'll write this as. It's C2 up here. And C3.
Yeah.
So our earlier interpretation, when we were thinking about the real space, is that it would be the area under the curve. So what do you have for your expectation about these two integrals? Are they the same or are they different?
they should be different. There's
Okay.
different
Different paths.
area, yeah.
Right, yeah, so that would be if you, right, and ignoring the fact there's a big old red mark in the middle. Right, if you thought about it with the context of area under the curve. And it very clearly, very obviously. Would mean that C2 would have a bigger integral than C3.
Yeah.
Is that correct? Okay. So hold on to that thought. Because it's wrong. Maybe, I don't know, we'll see. Do the work at home. But hold on to why you think that, right? That's from the real space. We're gonna have to discard it in the complex space. We won't have time to do it. So get it into a form like that, do those integrals and see what you come up with. Make sense?
Yeah.
And don't be surprised if it's the same integral.
Oh,
Fair?
fair.
Not that it makes sense, but is it fair? Yeah.
Yeah.
If you haven't filled out a SOTI, please do that.
Okay.